Today, on how it's made. Glass cookware. We blow the lid off the story of how they make it. Soap bars. We come clean with the details. Steel drums. They do a bang-up job at the factory. And firefighter uniforms, when safety's a burning issue. Pyrex is an idea cooked up by the wife of a glass industry scientist in 1913. She believed the tough glass used in lantern globes would be great for baking cakes in, so she baked one in some glass her husband brought home. The cake was a hit, shattering the notion that glass was too fragile for the oven. Today, you'll find glass cookware of various shapes in most homes, a true recipe for success. To whip up some dishes, a batch feeder pushes ingredients into a big furnace as they spill out of a bin overhead. Silica sand is the biggest part of the mix. It's a crystalline substance and it makes glass transparent. The batch also includes soda ash and recycled glass. Some of the other ingredients are a trade secret. The furnace heats the mix to the melting point, over 1500 degrees Celsius. It turns into molten glass that looks like lava. The glass, in this lava-like form, will spend up to 24 hours in the furnace. On its way out, mechanical shears cut it into gobs. The gobs slide down a water-cooled chute and drop into a baking dish-shaped mold. There are 16 molds on a rotating table. As it turns, the table delivers the gob-filled molds to a plunger, which presses them into the baking dish shape. Continuing to rotate, the table positions the molds under blowers. They cool the freshly molded glass so it holds its shape. A mechanical arm suctions up the glass dish and sets it down on another revolving table. Flames lick the glassware from burners above and below. The dish is exposed to a temperature of over 1000 degrees Celsius. This softens its sharp edges so that the rim is smooth. Next, hoses blast high-pressure air, cooling the dishes to solidify them, so that a mechanical arm can pick them up without ruining them. It transports the glass dishes to a conveyor belt. Further down, another arm feeds the dishes to a kiln, where heating and cooling cycles temper the glass. This is what gives Pyrex its strength. Now it's time to put a lid on things. A different plunger presses glass gobs into a lid shape. Every lid needs a knob, so a valve inside the mold forms it and then thrusts the lid up to be picked up by a mechanical arm. The arm flips its lid and sets it down on a conveyor belt. The lids are on the move, traveling through a tempering kiln. On their way out, a fan cools them off so they can be handled by human hands this time. Workers inspect each glass lid before packing them. On another line, there's a product that's made to measure. Little platforms lift the measuring cups to suctioning arms that protrude from a revolving silkscreen machine. A little squeegee forces enamel through a screen, printing measurements onto the cup. Over in the lab, a worker roughs up a sample dish. By rubbing it with sandpaper, he mimics years of wear and tear, but it's about to be subjected to even more abuse. He places a sharp tool in the center of the dish and takes aim with a hammer. Will it break without shattering into numerous little shards? It's a clean break, which means this dish has met the quality standards. Talk about raising the bar. The widespread use of soap has elevated our standards. Soap fights grime and it battles dangerous pathogens. It makes the world a more hygienic place. So you could say this product's reputation is squeaky clean. It has function and form. Soap comes in a variety of shapes, colors, and textures. But it all starts in a bubbling kettle, where animal or vegetable fat reacts with sodium hydroxide, a caustic substance, to create soap. They add water to keep it fluid, as steam bubbles up through the center to mix it all up and encourage the chemical reaction. This may look like an Arctic ice floe, but it's the leftovers, soap that's settled at the bottom of the kettle. They pour it all into this tank and reuse it in the next batch. Now they spray hot liquid soap onto a big metal roll. It solidifies in a flash, and a big blade scrapes it off the roll, creating ribbons of soap. The soap ribbons plunge into a hopper, where an auger moves the soap along, sending it down a chute. The soap ribbons fall all the way to the next floor, to big steel rollers called mills. They mix and compress the soap. A blade scrapes it off the rollers and cuts it into ribbons again, but these soap ribbons are denser. Inside the next hopper, another auger turns. It pushes the soap through an extruder called a noodle plate that shapes it into soap noodles. As the noodles fall from the extruder, they're collected in bins, which are then dumped into a mixer. At this point, they add color in powder and liquid form. Steel blades stir it up until the color coats the soap noodles. They add some fragrant oils, and the blades toss it all together. When the batch is ready, a trap door opens. The blades keep turning, nudging the soap out the door. Then it's forced through another noodle plate. This mixes up the batch a little more. Next, they push the soap through a forming plate, making a long bar. Blades mounted on a track slice it into shorter pieces called slugs. The soap slugs are on their way to the next stage. They're on a 2-lane thoroughfare, heading into a die press. A mechanical arm pushes the slugs through an oval plate, trimming it and then loading it into the die. The die rotates to accept the slugs. Mechanical presses move in to shape and stamp them. Mechanical arms suction the bars to remove them from the die. These mechanical pushers help. They nudge the soap bars out of the die towards the suctioning arms. The oval soap bars now travel through a wrapping station. A blade crimps and heat seals the plastic wrap in one fell swoop. Then automated grippers grab the wrapped bars and load them into a machine, which slides them into little boxes. Now it's time to pack it in and scrub up with the soap of your choice. The story of the steel drum begins in Trinidad in the 1930s, when street band skirmishes led to the ban of skin drums. So people improvised and made drums from thick bamboo poles, car parts, tins, and finally oil barrels. They came up with a whole new sound without skipping a beat. When people first started pounding on steel instruments, they inadvertently dented them. That's how they discovered that each dent produced a different pitch. So now steel drums are dented on purpose. To make a drum head, they cut a piece of steel into a circle. They weld a metal ring onto it, and then they position a metal shell or skirt on the ring and weld it in place. The drum is held in a big clamp, while a worker pinpoints the drum head's exact center. He places a measuring guide there, using it to mark radial lines from the center to the rim. Each line is 10 degrees apart. As the drum turns, he draws circular lines to make a grid. Now he pounds the head of the drum with a pneumatic hammer, using the grid as a guide to ensure the work is done evenly. It takes 8 hours of hammering to transform the drum into a bowl-like shape. This is called sinking the drum. Then, with a special guide for curved surfaces, a technician measures out another grid inside the bowled drum head. He outlines the notes that are about to be hammered out. In this case, a high B and an E. Then he hammers down the steel around each one to shape the note. Getting this right takes skill and a lot of time, up to 50 hours. He trims the drum skirt to the correct length and tapes a stencil of the company logo onto the skirt. This device is an electrical etching machine. It uses acid and electrical current to eat away the steel exposed through the stencil. Now, a technician wields an ultrasonic thickness probe. She presses it against a note. Using high-frequency sound waves, the probe measures the steel's thickness to within a fraction of a millimeter. She grinds down the notes where needed. Using a scribing tool, she scratches a line around each note so it'll be visible to the player. Now it's time to make sure they've struck the right note. To tune a steel drum, the technician plays a note with a stick and then dents it with a hammer to adjust the pitch. You have to have an ear for this job. He hammers the note until it sounds right. Sometimes he turns the drum upside down to knock out a note from the underside. For the fine tuning, he relies on an electronic tuner. A microphone delivers the sound to it, and the lines on the screen tell him if the note is in tune or not. Next, he burns the border of each note with a blowtorch. Then he cools it down with water. The process tempers the steel, making the notes more resonant. He tunes the drum again, checking for flaws. After the drum is chrome-plated, he tunes it a final time. It's taken 120 hours to make this steel drum. Now it's time to take a break and party to the steel band sound. Firefighters have been doing their jobs heroically for centuries. Their uniforms, however, were not always up to the task. Good thing today's firefighters are cloaked in layers of space-age material. The protective armor has virtually eliminated firefighter deaths caused by burn injuries. A computer-guided machine cuts out more than 90 parts to make the outer shell, just one of 3 layers in a firefighter's jacket. This fabric contains synthetic fiber known as PBI, which protects against temperatures as high as 648 degrees Celsius. Another machine tapes the seams of the jacket's middle layer, the moisture barrier. Pressure rollers and high heat activate glue in the tape, sealing the seams. This synthetic fabric lets perspiration through, but blocks some harmful liquids such as battery acid, hydraulic fluid, or infected blood. Now they line the moisture barrier with the thermal liner, the jacket's third and innermost layer. This synthetic fabric protects against heat of up to 426 degrees Celsius. To reinforce the cuffs, hems, and front and back panels, a worker sews them together with heat-resistant tape and thread, but she leaves the neck area unattached, so the firefighter can pull the jacket inside out to inspect the liner between rescues. Back to the outer shell. A worker sews 2 orange and silver stripes to the front and back panels. She also sews a stripe onto each sleeve. The fluorescent orange makes the firefighter more visible in daylight, the reflective silvers for nighttime or in the smoke. In some cases, she adds reflective die-cut letters identifying the fire department or spelling the firefighter's name. A strip of Velcro goes onto the left front panel. It's one of 4 ways to fasten the jacket, in addition to zippers, snaps, and hooks. To keep water from entering through the front of the jacket, they attach a strip of the same fabric used to make the moisture barrier. A worker sews it inside the outer shell's right front panel, what's called the storm flap. The storm flap's other side gets a Velcro strip that mates with the Velcro on the left panel. They attach the front panels to the back panels. A worker folds the garment over, and the machine sews through 2 layers at once. It's another way to reinforce the seams of the jacket. They use a different sewing machine to attach the sleeves. A worker sews 5 different seams to join the shoulder areas. This is critical because firefighters carry an 11-kilogram air tank on their back. The seams spread out the stress this weight places on the jacket. A worker attaches 3 metal snaps to the inside front of the outer shell. These will attach the outer shell to the 2 inner layers. Then, a heat-resistant plastic zipper. This machine applies 3 rivets to each of 4 spring-loaded hooks along the right front panel of the jacket. A 1.8-meter long strap cinches around the armpits to drag an injured firefighter away from danger. A worker then snaps together the assembled inner layers to the outer shell. There are 4 snaps on each cuff, which could heat up quickly in a fire. Tabs ensure they never burn the firefighter's skin. The front panels come together with 4 snaps on each side. The 10-centimeter collar unfolds, covering the neck to where it meets the firefighter's helmet. Fully assembled, the jacket weighs just more than 2 kilos. This testing device gauges how long it would take to sustain a second-degree burn. A gas burner shoots a flame that's 1,093 degrees Celsius directly onto the jacket's outer layer. A heat sensor mimics human skin's sensitivity to heat. The material fails the test if the transferred heat would cause second-degree burns in less than 17.5 seconds. Finally, they shower the uniform for 20 minutes to test its watertight seal. The dummy's wearing a cotton bodysuit underneath. Just one wet spot on the bodysuit, and the uniform fails inspection.